like. In chapter 4, lesson 3, what we're going to do is finish every single derivative possible. That's what chapter 4 is about. Okay, learning how to do the derivative of everything. So far you've learned how to do polynomials. You've learned how to do trig. You've learned about the chain rule and implicit differentiation. So these are the things that we have left. Not only do you need to know how to do trig functions, but you need to know how to do derivatives for inverse trig functions. So that'll be today. Then next week, we'll focus on 2 other kinds of derivatives that you need to know how to do. You need to know how to do e to the x and other exponential functions. So we'll learn how to deal with that and how to take derivatives of those. Just follow the rule. And we'll also learn logarithmic and how do you take the derivative if something has a logarithm in it. There are other derivatives, polar derivatives for polar coordinates, parametric derivatives. Those are all part of the BC curriculum. So if you're a junior and you opt to take this class next year, you'll learn about those. But those are the ones that we will do. And then as part of this chapter, we're also going to bring in a man named Francois L'Hôpital, and he was a French mathematician that came up with a rule for derivatives as well. So the rest of this chapter, including this little bit that we're going to pull in from chapter 9, is just all straight derivatives. Then we get to chapter 5, and chapter 5 is going to be all applications of those derivatives. Okay, so a lot of solving those real-world problems and where those velocity, acceleration, and area and volume and all that fits in. So chapter 5 will be the end of the derivative stuff. Chapter 6, we get into antiderivatives, which is doing everything backwards. Okay, good times, lots of fun to be had, but this is where we're at. Yes, antiderivatives. You never knew it could be so fun. All right, so today, 4-3. It's not A or B, it's just all one day's lesson. So the derivatives of inverse trig functions. So just so you know where we're going, what we have left to do, we're more than halfway through our overall curriculum for AP. All right, so inverse trig functions. They are defined as y equals, and they're written either as sine inverse of A, or sometimes you'll see it written as the arcsine of A. So the word arc implying the word inverse. So that can be applied to any of those inverse functions that you learned about in trig last year. What this does is it takes, in radian mode, it takes the pi, or it results in a pi value. And so you work everything backwards. So for example, if you are working on the sine inverse of what was the square root 2 over 2, the result of that is always the value of pi where that occurred on the unit circle. So an inverse just takes what you know about the unit circle and does it backwards. And so where does the sine produce a value of square root 2 over 2 on the unit circle? Okay, 1/4 pi. Now, doesn't that happen somewhere else also? Where else does sine produce a value of rad 2 over 2? Okay, also in the second quadrant. Okay, 3/4 pi. So you're going to have to watch, sorry, my 3 is not written very well. You got to watch the domain that you're given so that you know which window that you are, which quadrant you're supposed to answer from, because there are multiple answers to inverse trig functions. Another one, like tan inverse of 1. Well, that happens twice also. That happens at 1/4 pi, but it also happens at 5/4 pi. And again, you want to watch the domain that is specified so that you know which of the quadrants to pull your answer from. In fact, it could even be more than that. Okay, it could be 9/4 pi if they want you to go around the unit circle. It could be negative 3/4 pi. That's back in quadrant 3 again. So there are multiple answers, all determined by what the domain is. Now, if they don't say the domain, if the domain is not specified, then the default domain is quadrants 1, 2, and 4. Quadrant 3, as a default, is never allowed in inverse trig. It has to do with the original function passing both the horizontal and vertical line tests, and so quadrant 3 by default is not included in any domain unless otherwise specified. So unless it specifically says you are allowed to, the default is no. Okay, so if there is no domain specified, you have to assume you're only operating in quadrants 1, 2, and 4. Unless they give you a specific domain like something like this, that x can be between 0 and 2 pi. So if they do specify, then that opens up quadrant 3 for you as a possibility. Otherwise, assume you can't use it. Okay, now that's just a quick review. We did that in chapter 1. Way back in August when we were reviewing. Now we need to know how to do the calculus of this. There's not, you're just going to have to memorize them. Okay, just like you memorize that the derivative of sine is cosine, you just have that memorized. And there were 6 of them, and you memorized them. There are 6 for inverse trig, but they do come in pairs of 2 like trig did. Okay, everything comes in pairs of 2. Also, what was the thing about everything with co in a trig? Right, and same thing is true in inverse. Anything that's a co, so inverse cosine, inverse cosecant, inverse cotangent is also always negative. All right, so I'm just going to give you a list of the function, and then I'm going to pair it with its derivative. I don't know if that'll be enough room for me. Okay, so I'm going to group inverse sine of A, and I'm going to group inverse cosine of A together. Because the only difference in their derivatives is a negative. Otherwise, their derivatives is the same. So if you're looking at the derivative of inverse cosine, its derivative is plus or minus 1. It's positive if it's inverse sine, it's negative if it's inverse cosine, and the rest of the derivative is the same. The square root of 1 minus a squared times dA dx for the chain rule. So we had to learn about the chain rule before I could teach you this, because you needed to know that the chain rule is part of it. So that's something you're just going to have to memorize. The proof has to do with the Pythagorean theorem. We're not going to go into that. I'm just going to tell you this is the derivative. Yes, ma'am? Right, it's A is what's in the parentheses, so you take the derivative of what's in the parentheses. Yep, so whatever happened, I could have used any letter. It wouldn't matter what letter I used, but whatever's in the parentheses, that would be the chain rule. All right, the next set I'm going to give you is secant and arcsecant. So secant inverse of A and inverse cosecant of A. Those two go together as well. The only difference is the plus or minus. So their derivative is plus or minus 1 over. All of these have the same kind of pattern, or all plus or minus 1 over. Okay, give yourself, leave a little space in front of the square root. This one's got a square root, but it has something in front of it. This one's a squared minus 1 instead of 1 minus a squared, so it's backwards. And then it has the absolute value of a in front of it, times a chain rule of the derivative of whatever the value of a was in the parentheses. So those two both have a plus or minus 1 on the top. They both have a square root in the bottom. You just have to keep straight which order the subtraction goes. And then the last one is the pair of tangent inverse and cotangent inverse. So tangent inverse of A and the cotangent inverse of A. Again, they go together. They are plus or minus 1 over. And this is the only one that doesn't have a square root. And it's addition. It's a squared plus 1. So you don't have to worry. It's the simplest of all of them. It's addition, so you can't get the order wrong. There's no square root, so you can't mess that up. And then dA dx is the chain rule. So those are the straight derivatives. Just those are the 6 in pairs of 3 that you have to memorize. Your homework tonight is just going to be plug and chug. All right, do this derivative, do this one, do this one, do this one, just applying the rules over and over again until you get them really firm in your head. So we're going to do a couple of those together too, just to practice. So we're just going to do find f prime for the following function. For f of x equals the inverse cosine of the quantity x squared. And so this is really just going back to what the rule was and then dropping in x squared in the position of wherever a was. So my definition for f prime for cosine is -1 over the square root of 1 minus a squared times the chain rule dA dx. So sometimes it's helpful to just practice writing it down as you work towards memorizing it. And now what I'm going to do is the a value, the a quantity, is x squared. So I'm going to drop x squared into the position of every a here. So I'm going to drop x squared here. And then I'm going to drop the derivative of x squared right there. So this will become -1 over the square root of 1 minus. Now I'm dropping x squared into the a position, which is already also squared, so it would be x squared quantity squared. And then the derivative of that is 2x. That's the chain rule. It's the derivative of x squared. So to clean that up, this trig derivative is negative in the numerator, 2x, over the square root of the denominator, which is 1 minus x to the 4th. And so as you clean that up, you're squaring the square and then combining the numerators, and that's it. It's really just plug and chug, plug and chug. Okay, any questions on that one? All right, let's try another one. So in a similar way, find g prime for the following g function. Secant inverse of 5x to the 4th. And so for me, or for you, I would recommend right now, while you're just practicing, is just to write down the rule. So the g prime rule, because it's a secant, is +1 over the square root of a squared minus 1 in the opposite order, the absolute value of a out front, and dA dx as my chain rule. So just for practice, getting used to what that is. And then you're going to want to drop a, which is what in this case? Okay, 5x to the 4th. That a is going to get dropped in here, here, and then the chain rule is going to drop me right there. So that 5x to the 4th will take its place. So the derivative of g is going to be 1 over the absolute value of 5x to the 4th, the square root of quantity 5x to the 4th quantity squared minus 1, and the chain rule on 5x to the 4th, which is what? 20x to the 3rd. All right, so let's clean this up and see what we have. So my first derivative on g is going to be 20x cubed over, all right, now 5x to the 4th 5 is a positive number, so I can pull it outside. And then my square root will be 25. I guess I don't need that. X to the what? X to the 8th minus 1. Then I look to reduce. I could pull the 5 out because I was guaranteed it was going to be positive. And so that was fine for me to do that, which allows me to reduce the 20 and the 5. Be careful when you reduce variables, though. X to the 3rd, and then absolute value x to the 4th is reducible, but you have to remember to preserve the absolute value. So I'm going to have 4x to the 3rd in the numerator. Oops, I'm going to have 4 because I'm going to reduce. 4 over. When I reduce x cubed with the absolute value of x to the 4th, I'm left with the absolute value of x. Now, if I'd been left, if the reducing would happen differently, let me just take a minute and show you. If you had this, okay, if you had x squared reduced over x to the 4th, that reduces into 1 over absolute value of x squared. Now, x squared, you only need the absolute value if the number is going to be negative. And what do you know about something squared? It will always be positive. So when that is the case, when you come up with an x squared, you don't need the absolute value anymore. But if you had x to the 3rd over the absolute value of x to the 4th, and you reduce and you get 1 over a single absolute value, that's not, you need to keep that absolute value because it's not an even power of the result. So that's why I've got it kept. X is a negative number like -1.
Yeah, it's like -1 over 1. The answer is -1, but if you put absolute value for x, then it will be 1.
Right. When we're going to start plugging in some numbers in the future, and we'll start dealing with those situations. But for now, you can just leave it. Okay. So like in this case right here, you'll have 1 over the absolute value of x cubed, which needs to stay because it's an odd power. All right, so back to this. And then we've got 25x to the 8th minus 1. And that's not simple. You can't simplify that anymore. That's pretty much as far as you can go with that one. All right, last example. All right, so you are going to get so good at these. So find the normal line to the function y equals the inverse cotangent of x at x equals -1. So again, we need the point, we need the slope, which will the tangent slope, and then we need to convert it to a normal slope. So first we need the point. To find the point, we're just going to plug -1 in. So y equals the inverse cotangent of the value of -1. The domain is not specified here, so I can answer this in quadrants 1, 2, or 4. Cotangent has a negative value, a -1 value twice. It has it in 3/4, which is in quadrant 2. It also has it at -1/4, which is in quadrant 4. Someone else might think, well, what about could I use 7/4? That's also in quadrant 4. All right, now we did not have a specified domain, and so we've got to pick one of those as the best answer. Right away, I'm going to eliminate 7/4. The reason I do that is because to get to 7/4 on the unit circle, you have to pass through quadrant 3. And quadrant 3 is prohibited in any form in inverse trig. And so 7/4, because I would have to go around through quadrant 1, around through quadrant 2, through quadrant 3 to even get there. Okay, I'm going to eliminate that. So now I have two viable options. 3/4 is in quadrant 2, And negative 1/4 is in quadrant 4. And the rule for inverse trig is you pick the one that's closer to 0. Okay, in terms of just pure net distance, the one that's, if you have two viable options, you pick the one that's closer. And so negative 1/4 is closer to 0 pi than 3/4 is. So that's going to be the one that we choose for our point. All right, then we work through the tangent slope. And so the tangent slope would be y prime. And this is negative 1 because it's inverse of cotangent. And then you can go back and look. You're like, okay, it was a squared plus 1. And right now that's just x squared plus 1. So I can plug the number negative 1 into that. So I'll have negative 1 over negative 1 squared plus 1. So negative 1 over 1 plus 1, so negative 1/2. And so that's the value of my tangent slope. And then to finish this up, I'll just convert it to a normal slope. And so the normal slope is going to be the value positive 2. And okay, good asking. Yes, and I got a little sloppy. Okay, the chain rule here. What is the chain rule when it's just x?
Oh,
1.
Sorry.
Yeah, no, so you should always discipline yourself to do that. It's really good that you pointed that out. I just got a little bit careless because I knew it was going to be 1, and so yeah. All right, so we have our normal slope, so now we can write our normal line, which would be y minus the negative 1/4 pi is my y value, the normal slope of 2, and x minus negative 1 is my x value. So y plus 1/4 pi equals 2 times x plus 1.